Today's physics colloquium is a very exciting topic. I'll tell you about that in a second. We have wine and cheese afterwards, which will be at the Bridge Annex patio, so just join us there directly after. So today it's my great pleasure to welcome Professor Sara Seager from MIT. Sara is one of the pioneers in the search of life beyond our own solar system. It has defined much of what it means to think about exoplanets science and how to look for signs of life. She got her PhD in Harvard and was a long-term member at the Institute for Advanced Study. She was a research staff member at Carnegie Institution and then went to MIT, where she's been ever since. If you actually look at the list of her job titles, it's quite impressive. It's Professor of Physics, Planetary Science, Aerospace Engineering, the class of 1941 chair. And if you talk with her, she'll tell you she also runs her own chemistry lab. So there should maybe be one more included in that list. That reflects her unusual combination for cross-boundary approaches to the search for life beyond our own solar system. And really, her research has covered a wide range of many of those topics. She's been the Deputy Science Director for the Transiting Exoplanet Survey Satellite mission. She's worked on multiple concept missions for search of exoplanets, including the Starshade mission. She's been an advocate for the search of life on planets of our own solar system and also beyond. She's the lead of the Venus Morningstar mission. And we'll tell you, I think, more about how to exactly look for those in atmospheres in her talk. Her honors include the MacArthur Fellowship. She's been elected to the National Academy of Sciences, the Kavli Prize in Astrophysics for pioneering work on exoplanet atmospheres. She's an officer of the Order of Canada, and many more accolades that I don't have time to list. But I'll hand it over to Sara and let her, tell herself all the great things that she's worked on and is thinking about.
Thank you.
Thank you.
Thanks. So the search for signs of life beyond Earth begins billions of years ago when a simple single-celled bacteria, cyanobacteria, figured out photosynthesis, how to harness energy from the environment. And in the process generated oxygen, a waste gas. So you all know we need oxygen to breathe, and oxygen fills our atmosphere to 20% by volume. But without life and without plants and photosynthetic bacteria, we basically would have no oxygen. It's so reactive, it shouldn't be there at all. So what's really interesting is about 100 years ago in a textbook, the astronomer Jeans, that you know from like Jeans' escape and the Jeans theorem, wrote a few paragraphs, like let's say 1 or 2 paragraphs on this, first kind of proposing the idea that you could look for oxygen on another planet and have some signs of life. And in fact, he also took his telescope to look at Venus, our sister planet, and had to put an upper limit, of course, because telescopes weren't that good back in those days. So now we want to find gases on exoplanets, planets around other stars, gases that might indicate a sign of life out there. Now, my first visit to Caltech was almost like 25 years ago. I want to say it was around 2002. And it was almost, I'm looking at the people who were here then, it was almost inconceivable to hire in exoplanets back then, because there were just like maybe 40 exoplanets, there were maybe 2 transiting planets. It was so hard to see where we are today. So I have a phrase about that. I like to say that in the search for signs of life beyond Earth, there's a line between mainstream, what is mainstream research and what is crazy. And that line is constantly shifting. So back then, it was kind of crazy to work on exoplanets. It just seemed like the field would peter out. Our detectors weren't good enough. Our software wasn't good enough. To today, legit having people thinking about signs of life on exoplanets. I'm just saying all that because I'm about to take you on a journey that is definitely on the side of crazy. So to start with that, our planet Venus has a lot of atmosphere anomalies. We can't obviously say that there are signs of life there, or I don't know, maybe it's not obvious, people want to say that. But I have like this short list for you. And these anomalies are from, most of them quite a long time ago. There's an unknown absorber that absorbs half of all incident sunlight. And there's a lot of contenders for what that molecule might be. We don't know. There is past evidence for non-spherical particle in the clouds of Venus. We'll come back to that. There's gases. You may have heard of this reported very controversial report of phosphine on Venus. There's past probes that went down in the atmosphere that did actually detect a tiny bit of oxygen at parts per million level that's not explained. And there's this kind of whole case for anomalous gases on Venus. Some are more robust than others. But I think it's fair to say it's worth going to Venus to take a modern look with modern instrumentation. So what I'm going to talk about today are the Venusian clouds, a possible habitat. Then I'm going to talk about novel ideas for space missions to Venus, to search for complex organic molecules, to search for signs of life in the clouds. Then I'm going to talk about a compound I hope at least some of you have heard of, but you will remember it after I tell you about it. It's called an ionic liquid, and I'm going to try to explain how that may also expand the exoplanets out there that might be habitable. So first about Venus, I'm going to start simple, that you all know this already, but it has a massive carbon dioxide greenhouse atmosphere. So the surface is 700 Kelvin. It's too hot for life. But just like on Earth and most planets, the temperature drops above the surface. So 50 kilometers above the surface of Venus, it's the right temperature for life, actually. And it's a bit of an aside, but it's also the same pressure as here on Earth. So in the clouds of Venus, it is the right temperature, it's the right pressure it's the right temperature for life. And there are liquid clouds up there. And it turns out that Carl Sagan first proposed half a century ago for these reasons, maybe there's life in the clouds. Now, I wasn't around back then, and so I would love later to ask Professor David Stevenson what was going on back then. No, people didn't know the clouds are not water. They're made of concentrated sulfuric acid, a chemical that's very, very dangerous for life. But anyway, let's just continue the four arguments. We have life in our atmosphere. There's bacteria that get swept up. They go into the cloud particles. They may not want to be there, but they're there until they rain down. And so there's definitely a case worth thinking about with these anomalous gases, with the right temperature, with liquid and energy, to revisit this idea of possibility of life in the clouds. Here's a schematic, a cartoon, showing you altitude above the surface. And it's also showing you temperature and pressure, just so you can get your head around what we're talking about. An extensive vertical cloud layer of, say, 15 to 20 kilometers deep. It's always there. It's not like convective clouds here on Earth. There's like a permanent cloud cover always present, not fragmented like here on Earth. And you can see like the temperature and pressure. So these are concentrated sulfuric acid. There's very little water. There is a bit of water in the cloud particles. It's so locked to the sulfuric acid that it's not really available. And so that's kind of where we're at today. So I'm just going to start with the biggest problem that I see for life in the clouds of Venus. And that problem is, how can life persist aloft? Because down in the bottom of the planet, it's just way too hot. So I want you to think for a moment about the droplets on Venus. We have measurements from the Pioneer Venus and other probes that give us a handle on the particle size distribution. And people have to make models, like cloud formation models, like particles grow, they nucleate, they coagulate, they grow, they settle out. And this has to end up matching up with the observed particle size distribution. So part of those models you can pull out, and this is from Peter Gao, you can actually pull out like the lifetime of the particles, because they want you to imagine if there is life in the clouds, that life has to propagate, right? But if the particles coagulate and grow and eventually sediment out, it's kind of like a non-winning scenario here, because any life, like, it has no way to stay aloft indefinitely if it's all going to rain out. So this is just showing you the lifetime of particles. So you have altitude above the surface, particle size. So many of the particles are about 2 microns. And you can see from this color bar, particles can last, a year, 10 years, or less. So they can last long enough. You could imagine life is up there. But actually, you might wonder, maybe they can fragment. And if cloud particles could fragment, now life that exists and reproduces can spread all around. But no fragmentation is happening in these Venus clouds. It turns out you can think about on Earth, I showed, this is just a picture I pulled out to remind you, like our raindrops, they get so big and they flatten out because they're moving very quickly when they get to the bottom of our atmosphere. And there's hydrodynamics, like just from the difference in airflow around the particle, just destroys these raindrops and makes them fragment. But I just put this little equation there for you. It is the Weber number. It captures the disruptive hydrodynamic forces compared to the stabilizing surface tension forces. But in the bottom corner, in the bottom right, I showed you like the difference on Earth. Some raindrops can be as large as 1,000 microns. On Venus, they're like 2 microns. So the particles are much smaller. On Earth, velocity can get really high, like 8 meters a second. On Venus, they're just like a tiny, tiny velocity. So you never get there. So the question becomes, how could life stay aloft? And we came up with, like, admittedly a bit of a hand-wavy theory, but I just wanted you to know about it because it is like the physics question about life on Venus. How can life stay aloft? And we just came up with this scenario that as the droplets coagulate, they get bigger and eventually they settle down. But it gets hotter and hotter. And so this excess sulfuric acid would eventually evaporate. And you may be, if there is life in the clouds, it may be left over like spore-like things hanging out beneath the clouds. And indeed, there is a layer of unknown haze. But now we have to ask, how would these particles get back up to the clouds? And then we invoke something called gravity waves. They're not gravitational waves, but gravity waves. Has anyone seen them before? I put a picture there. So you can look for this like the next time you're on the plane. But winds will like hit the side of a mountain and create a vertical wave. And that wave, like on Earth, will break. And then it goes like horizontally, up, down, up, down. And if you get lucky, you can see like this striped cloud pattern. I always look for it when I'm on the plane. So we have real evidence of gravity waves here on Earth. They've been seen on Venus from orbiters. And this is a way to like nudge particles like back up to the clouds. And I just kind of gave you this little snippet to let you know we're thinking about it. We don't have all the answers. We're just trying to motivate the case to go to Venus to look for signs of life. And I partly wanted to give you like a negative thing, like, hey, how life can stay aloft. We have some ideas. We don't know exactly how it would happen. Because the thing you would normally want to dismiss the idea of life in the clouds for, I'm here to convince you that that reason is not a bad reason. It's okay. And that is the fact that the Venus clouds are not made of water. They're made of concentrated sulfuric acid. Now, I know we have a lot of theorists here, but how many people have ever used concentrated sulfuric acid? You know what? Okay. And I bet you if there's people who work in the lab here, you're using it to like clean your electronics and kill life. You're not using it for a good reason. It's very dangerous. And just in case some of you don't know how bad it is, and also we're trying to unpack maybe what is the main reason why people would never believe there's life in the clouds of Venus. And it has to do with the sulfuric acid. And you know, our DNA will not survive in sulfuric acid. So therefore, our life cannot survive. And we actually can break this down. I didn't invent this. I just took my own video. I just wanted to get a good video to show you. But if you look at this cartoon of our DNA, it's to remind you our DNA has a sugar phosphate backbone. So I'm going to show you like this canonical demo of mixing sulfuric acid and sugar. So that sugar is just like the sugar you get from your house. But that sugar represents DNA, which represents life. Okay, are you with me on that? So this is why like you could never believe there's life in the Venus clouds. So I'm just I've sped this up to 2.5 times. That's me pouring sulfuric acid on the sugar. You can see the infrared on one side, and look at the infrared right now. It's getting hot. And look what's happening to that sugar. Remember, that's our proxy for life. It's not pretty. You know, if you look what's happening, yeah. This is an exothermic reaction. It's really hot, very hot. It's messy. What's happening is it's like a dehydration reaction. You're seeing the sulfuric acid is reacting with the sugar, and it's giving off sulfur dioxide. It's giving off water vapor. And eventually, this thing turns into basically like dried out carbon. Now, I'd like to, if you ever want to come to my lab, I'll give you a tour. I'll show you this. We don't really let people like touch the outside anymore or smell it, but one of our visitors wanted to actually smell it. Yeah, and you know what? It smells like cotton candy. Yeah, so that's kind of bad news. So remember, I read about this, I picked up this quote decades ago, and I've always used it as my guiding light. You know, so what would you do about that? You'd probably not join the kind of fringe group trying to keep alive the idea that there might be life in the Venus clouds. Well, just a long story short, we started experimenting with concentrated sulfuric acid. And one of the first things we did was we took our 20 biogenic amino acids and we put them in concentrated sulfuric acid. So unlike sugar and unlike our DNA, we discovered that with one exception, all of our amino acids are stable in concentrated sulfuric acid. Some of them are chemically modified, but on the whole, they're stable. So I like to tell this to like my astronomer friends, but I had to learn laboratory chemistry, and we do NMR, nuclear magnetic resonance spectroscopy. And this is like I showed this picture here of this shared facility that's like these NMR. It's like a giant magnet, and you send a radio frequency pulse into your sample, and you're exciting the nuclei of spin 1/2, and then they relax back down and they give you a spectrum. That's what I'm showing you there. It's intensity versus a chemical shift. But unlike in astronomy and exoplanets, we have very noisy data. Our signal is so hard to drag out. But here we have very strong features. You don't even see noise. These are 3 features. And here you can see one of the amino acids. It's called alanine. I had to learn a lot of organic chemistry, and I know there's at least one person who understands organic chemistry in the audience, but one of the failures is that they never put the carbons. If there's like a carbon at 1, 2, 3, yeah. So you're just supposed to know that they're there. So I know if you're a physicist, your mind isn't like naturally attuned to organic chemistry, but there you have it. So what I'm showing you here, I'm actually just trying to give you one data set to show you why we know the amino acids are stable. What you're seeing here are the 3 carbons, 1, 2, 3. They each get a different shift because the signal depends on like the environment of the electrons. If the electrons can like shield the nuclei, they get a different perturbation due to this magnetic field and the radio frequency pulse exciting the nuclei. So you can see the 3 different carbons, 1, 2, 3, and there's actually 3 superimposed data sets here. One is concentrated sulfuric acid, one is 81% sulfuric acid by weight, the rest water, and one is just acidic water. So in fact, this amino acid, it actually has the same signature in the 3 different solvents. And it looks the same, it is intact, it is stable in concentrated sulfuric acid. And so here's like just a picture of all the 20 amino acids. You can just look at them, and the ones with red or blue, those are the ones that are chemically modified. But the goal is for you just to see, you know, that on the whole, they are stable in concentrated sulfuric acid. Our goal is so my initial goal with this was only related to missions to Venus. And my original goal was to show that we can find, or synthesize rather, a DNA-like molecule. Not our DNA that is unstable, but just to simplify, like swapping out parts. Because I bet if I could come to you and say, I've got a DNA-like molecule, an informational polymer, that is stable in concentrated sulfuric acid, I know I would have your support to send a mission to Venus to look for complex organics. So it's been like a long journey towards doing that. And there's a lot of threads that are too complicated to explain here. But we definitely made a really nice milestone towards that goal. And we found that a single strand of a molecule called PNA, peptide nucleic acid, it's not DNA, it has a different backbone linker system, it's called PNA. It actually is stable in concentrated sulfuric acid. And this is like a step towards finding an informational polymer that is stable in sulfuric acid. The single strand we made, we actually synthesized, we found I'll just tell you this part of the story because I literally have been like switching fields to this. So we looked for like a company that could synthesize molecules that my team, I have a couple of biochemists on the team, had the idea. So we reached out to something like 20 different companies. You know, maybe half responded, maybe 6 took it seriously, 4 got on the phone with us, 2 sent us a proposal, and we found this company called Samaras. They're like this international drug synthesizing company, and they've been working with us all along to do this. So they will synthesize the molecule, we would usually test it. But in this case, the molecule is unstable at over 50 degrees Celsius, and the atmosphere of Venus, you know, it has a big temperature gradient. So we still have a lot of work to do, but I'm trying to convince you that we're on our way. Now, one really interesting thing is, like as an astronomer, astrophysicist, my main, like honestly, from that viewpoint, I just want to know if these molecules like are intact in sulfuric acid. Like that would be, I hope that like the physicists would agree, like I want to put a complicated molecule in, I want to know that it's intact. But the chemists wouldn't see it that way because, you know, acid wants to donate a proton. And the nitrogen atoms, they really want to receive a proton. So they're all getting protonated. And the chemists would want to know like exactly what is getting protonated where. But just like any project you might embark on, if you find something new and you kind of ignore it, it always comes back to bite you later. And your progress will slow unless you try to unpack every last thing. So we had to figure all that out, like where are the protons going, what are they doing? And it's getting very protonated. And the problem for us there is that it might interfere with the hydrogen bonding because the DNA, you know, the double helix, it's hydrogen bonding together. So we have kind of gone off on a whole tangent to explore something called alternate nucleic acid bases. Not our bases, but there's a whole lot of other nucleic acid bases. They bond together from van der Waals forces or other things. And I literally could give an entire talk on organic chemistry and concentrated sulfuric acid, but I won't do that. I will just maybe briefly mention one more thing in this summary slide. we were kind of on a journey to do some laboratory work to support the missions. And one more experiment we did, we asked Jack Shostak and his postdoc Daniel Duzovich to start this for us, was in the origin of life, people put lipids with polar heads in water to try to make a vesicle, like a spherical vesicle that would be like the first and most primitive step towards a cell membrane. And we wanted to also see if that could work in concentrated sulfuric acid. And so the first molecule that my colleague Janusz Petkowski and Daniel Duzovich chose, the first kind of set of 2 molecules, put it in sulfuric acid, and it formed these spherical vesicles. And that's what you're seeing in the bottom right. It is put a dye that got taken up, that itself is stable and got taken up into this mini vesicle. And wow, I mean, it is pretty amazing about what can happen in sulfuric acid. Now, oddly enough, in some fields, people would say, oh, there's no new idea. It's all kind of stuff that's been done. Oddly enough, this one experiment, people had done this in the past. And there was a time when sulfuric acid in chemistry had kind of a heyday decades ago. And people were studying like vesicle formation in concentrated sulfuric acid, not related to Venus in any way. So, okay, to summarize this part of my talk, Venus clouds, a possible habitat, one of the frontiers in the search for signs of life beyond Earth. Venus clouds satisfy the criteria for life. There's liquid, energy from the sun, and suitable temperatures. And I just gave you the most brief glimpse into this idea that sulfuric, I didn't say there's life in sulfuric acid. I'm just choosing my words carefully here, just to say that sulfuric acid is a possibility to host biomolecular building blocks. So what are we going to do about all this? Well, we want to go to Venus, to go into the atmosphere with modern technology and try to find out, are there these complex organics? Are there any signs of life? And maybe even one day, life itself. So we want to, the former Soviet Union sent over a dozen probes down into the Venus atmosphere. NASA's Pioneer Venus was 4 probes that went together down into the atmosphere. And there's some new missions being planned to go. There's NASA's Da Vinci, NASA's Veritas, there is European Space Agency. There are a number of other concepts like kind of on the table. But I'm leading my own thing to go to Venus because this idea of search for life, it is too taboo for large government agencies. People will not take it seriously. I managed to convince the organic chemists in astrobiology that it's legit. But it's still really hard to parse, like the idea that there could be life there. So I'm proud to lead and this consortium, we call ourselves Morningstar Missions to Venus. And in fact, we were self-motivated by the controversial phosphine discovery. When that was all unfolding, this was like in like 2020, I managed to get a small amount of seed money to study what kind of missions could we send to Venus to search for signs of life or life itself. I know the pandemic was really rough time, but one thing that helped was we had everyone's attention. And you know how if you have a team and you have meetings and a lot of people they can't show up all the time, but people could show up all the time. So we came up with 3 ideas. It was kind of like small, medium, large, short-term and cheap and not that capable, medium-term and more capable, and like far future, really capable. That would be sample return in the far, far future. So we got together and we would have these concentrated meetings. And I purposely chose my team to only one person had worked on Venus. And I also tried to avoid the cranky older people. And I wanted to have like fresh voices and think about it from a fresh perspective. And it was like a ton of work. But I'm now going to tell you where we're at for these missions and what we're trying to do to go to Venus in like a private-public partnership to do this kind of crazy search for molecules or signs of life. Our first mission to Venus, remember, small and just kind of not very capable, but a small mission. It's called the Rocket Lab mission to Venus, because this is largely Rocket Lab, building the rocket, building the cruise vehicle, the probe, and inside the probe is the pressure vessel. So I wanted to update you where we are with this very condensed summary slide. On the top left, you can see our actual probe. That is like the real flight probe. It's like just, about this big, and it will weigh maybe about 30 kilograms, maybe 25 kilograms. NASA Ames generously gave us and adhered the heat shield. That's what you can see on the bottom. On the top, it's the tiles the tiles that they had on the space shuttle and such. That orange is just like a protective tape. And this is like a small, cheap mission. It's not going to be an entry vehicle that opens in Venus. This probe is the thing that's going to be dropped off. No parachute. It's going to slow down on its own drag, by its own drag, and it will last for 5 minutes in the clouds. And we have a single instrument, which we call it an autofluorescent nephelometer. That's a picture of it in the top right. It is actually, I really think it's such a great picture, it almost looks like a model. That's the real picture, and what it's going to do is shine a laser. It says laser port. You can't really see the laser. We'll shine a laser through window. Our focal length is like 20 centimeters away because we're trying to avoid the airflow around our probe. And it's going to do two things. One is it's a laser at 440 nanometers. We're going to look for autofluorescence because pure sulfuric acid shouldn't fluoresce. Organic molecules, especially ringed molecules, aromatics, they fluoresce very easily. So this will be like not a definitive, there's definitely organic molecules, but it will be a sign of organic molecules in the cloud particles. We're also going to measure the backscattered polarized radiation from the cloud particles. Now, some of you may know that no particle in nature scatters equally in all directions. If you went around like shining a light at like a dust particle or a raindrop, well, raindrops make rainbows. It's concentrating the light and also spreading it out at the same time. So there's a lot of information contained. And prior missions had sent backscattered just intensity, the Pioneer Venus mission. And we're partly going back to confirm that some of the particles are not spherical, they're not pure concentrated sulfuric acid. That's a kind of whole other story to get into, but we've been really working hard on this. We have done some field testing. Professor Chris Carr at Georgia Tech got some NASA money, and that's the bottom left. Putting this instrument we call the AFN, autofluorescentnometer, like inside here, this kind of light aircraft / drone, and flying it around on the outskirts of the volcanic fog to like not only do our systems engineering, but data and analysis. On the bottom right, we also have a version of our instrument that is in the laboratory. This is in Colorado in Maggie Tolbert's lab. And there we're just like testing a lot of different sulfuric acid with different components put into it. And one of my students' entire PhD thesis just got condensed to this little square, showing you that the science and the measurements will be solid, but the interpretation is ambiguous, degenerate. You have to do retrieval to like capture all the possibilities of the refractive indices that are there. Now, I know everyone here has like your own project. I plead with you to make it somehow like archived and like lasting for decades, because we go back to try to interpret the Pioneer Venus data, and it's really hard. It's challenging to use someone else's data. It's not documented well. We are finding interesting things. We're revisiting that in the prior years, people had challenged some of that data interpretation. But that's where we are with this mission. Our target launch is 2026. We're going with Rocket Lab. And if we miss that date, usually the windows are like every 18 months. So the mission I really want to send to Venus, that's what I'm going to tell you about next. And that would be a parachute mission to Venus, where we would, parachute missions have gone to Venus before, but we would send a mission to Venus that would have like a probe, and it would just, instead of spending 5 minutes in the clouds, it could spend a lot longer. It could spend like an hour in the clouds, or 15 or 30 minutes. There's like a trade-off between size of parachute, mass of probe, and time in the clouds. And you really just have to optimize for, going the minimum time you need so that your parachute can be as small as it can be. But what's new here is on this, this is like just a CAD drawing of our entry vehicle that itself would have like a little parachute, so it would pop it open. And we have this thing, we're calling this an aerofairing. So here you see pressure vessel, high gain antenna. And on the bottom here, this is new, you wouldn't have seen this before. We want to have these miniature sensor patches. So what I want to envision is a mission that literally has 10,000 sensors, miniature molecular sensors, each of them designed to target a specific molecule. Now, in planetary missions, commonly people will send a mass spectrometer, where the mass spectrometer sucks in gases or solids. It usually pyrolyzes them and ionizes them. They often get fragmented, subject to a magnetic field, and then the path, they get separated out by their mass and charge. But these mass spectrometers tend to like vaporize. They tend to remove you really far away from that original molecule you're looking for. And we've also been exploring that concept. But we're trying to find like the most foolproof method we can to identify a molecule or a really specific class of molecules. And so we've spent some time exploring what all of these ideas could be, actually. And many of them are kind of ready, but they're not quite there. Like a lot of you know about chip-based frequency combs. I'm sure that someone here is working on those, like little photonic chips that are tuned to be designed to like match up with a very specific molecule. I heard when I came here, I just met Professor Judy Su. She's on sabbatical here. And she has one that looks amazing called frequency locked optical whispering evanescent resonator. And essentially, it's this little microtoroid that you coat with like a molecule that yours will bind to, and it amplifies the signal. And you can get down to like literally individual molecules. We spent a lot of time on carbon nanotubes. These are little tiny tubes that are very highly conductive. And this is showing you like a little cartoon where they're acting like a circuit because they're very, very conductive. But what people do is they add a molecule onto the carbon nanotube, and then it becomes like a puzzle piece. And if it matches up with the molecule it's targeted for, the electron configuration changes, and the resistance, the conductivity will change. So people essentially try to use these as like chemoresistors. They use them like in the lab. People have other models they use to try to detect like cancer cells in blood. And what I'm showing you here is like a little matrix from an MIT professor, Tim Swager. And what it's showing you is a bunch of different molecules of interest on the x-axis here. So you'll recognize, for example, benzene. And here showing you carbon nanotubes designed to interact with their target molecule. And this is showing you can think of this like change in resistance. So you can see where it lights up red, that's a win because your carbon nanotube was designed to see this molecule and try to identify it. And it's kind of a matrix. So I just want you to imagine like a new type of space mission with miniature molecular sensors, all targeted to find what you're looking for. And you have your classes of molecules, are stable in sulfuric acid, have your list of molecules you're looking for, and that's what we're trying to do. Now, many of these sensors, they're not ready yet. I learned how long it takes it takes a long time from an idea to something that actually works out. So this summer, we did something a little different. We wanted to move the idea forward, but it really is like 100 steps from concept to implementation. So we sent up not 10,000 sensors. We instead just did 32 sensors, like enough sensors to have to start thinking about the multiplexing problem. And these sensors, you can see it's on a box about like this. Those are really just temperature, pressure, humidity sensors. And here on the other side, you can see the battery, there's a microcontroller, there's a couple of other sensors. And we put this in a box. Hopefully you can guess where this is going. We put it in this box. It's a styrofoam cooler. Here's a GoPro camera. My master's student, Claire, in Aeroastro, she worked for Blue Origin for 3 years, working on parachutes, like for re-entry on Earth. And she designed this. She told me that the Pioneer Venus mission, like literally just like a month before launch, they had to completely change their parachute design because it was going to get like completely shredded in the Venus atmosphere. And she designed this ribbon parachute because as it's kind of going down, air can flow through it and it's less likely to shred. So she designed a parachute that's scalable to what we want to send to Venus. She got the polyester, laser cut the strips, and she literally sewed it together on her sewing machine. There's our parachute. So we put all of this together this summer in like a first step before our miniature molecular sensors are ready, and we launched it. We launched it on a weather balloon. And it turns out, I know that many of you here, you've heard of or you're involved with amateur astronomy groups. Did you know there's also amateur weather balloon groups? And Claire connected with them. They're like half an hour outside of Massachusetts. And there's a bunch of kids cheering because there was also like a summer camp for kids at this place. And the weather balloon, you know that it's filled with hydrogen and it's going to expand, right, as it rises because it's got to match the pressure outside. So what happens eventually? It's going to rise and expand and pop. It's supposed to pop, and we were going to go to about 30,000 feet, but the person helping us who runs the society, he said since our payload was so heavy, he had to put extra hydrogen in, and we went a little too high, in my opinion. We went to 70,000 feet, That's our picture from our GoPro camera. Like, why is that a problem? Because, you know, if you go to space, everything has to be like just perfect. And one of the problems is freezing, because when water freezes, it expands and it can break things. So in fact, our GoPro camera just stopped working before it got to 70,000 feet. And interestingly enough, our other GoPro camera, our second camera, failed before launch because it was one of those really hot 90-degree weather days. It was just so hot, and we had to wait around to get it to work. Another couple of interesting things I'll mention. This Weather Society, they're very sophisticated. First, you wait for a good weather day because you don't want your balloon like drifting out over the ocean. And we had no way to do telemetry, so we needed our sensors and our microcontroller that was recording the data to like last. And secondly, you're checking the predictive software like constantly, like, you know, minute by minute, literally, because you want to predict the path of your balloon so it will like land somewhere, not land like on private property, land somewhere good. So, and they also have a ham radio. Anyone here a ham radio license? See, I actually have my ham radio license. They have a ham radio. And the person's 14-year-old son, he now has his own business making trackers. So if you have a ham radio license, he can make a tracker, and that tracker is also attached to the balloon. So the middle picture is like an app that these amateur weather balloon folks use. And you're just tracking it because it's got the, it's pinging you if you're like a ham radio. And yeah, you're tracking this app, tracking where it is. So we did recover it. It landed in a tree, which was great news because it was kind of bordering a swamp. And here's Claire, her parachute like lasted the whole time. Our miniature molecular sensors, or our humidity, temperature, pressure sensors all worked. This is Eddie Hernandez. He's an undergraduate actually at Harvey Mudd College who was working at MIT for the summer. He's showing you here his microcontroller was working. So we're pretty excited about that. We're just trying to get ready so we can send up some more sophisticated sensors up there to detect things in the in the atmosphere, to detect particles, maybe to detect organics, to detect volatiles and things like that. So we're ready to go doing more experiments soon. Well, it's kind of part of a longer story. I've just been investing my discretionary funds in different things to go to Venus. Here's a balloon. This is like a 2.5 meter engineering unit. And I'll leave the rest about Venus for questions for later. But the second part of my talk, to summarize, they're novel pathways, missions to Venus. We can have small focused missions that only can exist because they're complementary to NASA and ESA missions that are doing the bigger picture of the environment of Venus and its history. And that enables us to just go after like a single question in a single focused mission. So we have the first mission ready to go. I showed you the hardware. We're planning for our second mission. We're ramping up to fundraise and to get ready to have a small series of missions to Venus to search for complex organics in the clouds. Okay, so I talked about the Venus clouds as a possible habitat based on laboratory-based experiments of organic molecules. I gave you a glimpse of the Venus work that the laboratory work was only meant to initially support. And that laboratory work has now taken like an entire life of its own. And now I'm going to get to what's my favorite part of the talk. Because, you know, once in a while, you just get so lucky. It's a rare moment to find something new, or at least in a very new context. And I'm going to now unpack for you what my team has uncovered and what it might mean for habitable exoplanets. So there are just so many exoplanets. We have a lot of amazing exoplanet astronomers and modelers here in this room. I'm not going to rehash everything for you. I will say, though, that our James Webb Space Telescope is really doing well for like mini Neptune, like small planets in between the size of Earth and Jupiter. It's doing well for Jupiter-sized planets. But it's also really on edge for helping us understand really small rocky planets very close to the star. This is kind of where the Webb can shine. It can help us understand where these planets came from and what happened. And I just wanted to give you a bit of background with this graphic. It comes from Kite and Barnett. And this is time. It's showing you time. It's showing you that we think planets are born with like liquid magma oceans. And in this case, it's arguing for like an H2-rich atmosphere initially. We have like nebular accretion, comets and asteroids hitting it. But at the same time, there's XUV, there's extreme X-ray and ultraviolet radiation coming from the star. And there's a lot going on because over time, after it's formed and been bombarded and energy delivered to the planet, it's going to cool. And like on Earth, you know, eventually you're going to freeze out and get like a solid surface. So that's what this picture is showing you. But, unlike Earth and Venus, there could be, and people are expecting there to be planets that they lose their atmosphere. And they have, as the atmosphere has been escaping, volatiles in the mantle are also coming out and escaping. And there's some moment in time where the atmosphere and the magma, they're exchanging gases with each other. But at the end of the day, you can have very different planets, like from Earth and Venus. You can have planets where the most volatile elements have escaped. But what's most soluble is sulfur compounds and water vapor. And those are kind of like the last things to boil off, so to speak, and they can be trapped in the mantle. So I want you to have this picture in mind for a moment, because we're so fixated on water as a solvent for life. All life needs water. But we can now also ask ourselves a question: can planets too warm for water host a liquid? So I'm now going to backtrack to the story, and I've already told you it's an ionic liquid. But my postdoc, Rachna, she's there in the front, and this is in my lab. Her fume hood's actually the one in the back. But when we were thinking, she's an engineering PhD from Purdue. She's now a professor in India, but she's an engineer, and it really helps to have an open mind. So we have some ideas about going to the Venus atmosphere, capturing the cloud particles, evaporating the sulfuric acid, because we may need to concentrate what is hopefully in those droplets. If there is life or some sort of microbial life, we want to get rid of the excess sulfuric acid for some experiments, concentrate whatever's left over. So when you're doing things for space, you just start out with something generic and clunky. She put together this evaporator system. Sulfuric acid has a very high boiling point. So we need to think of a low pressure system so it can evaporate more easily. So she put something together, and in fact, the only special thing about the system was the pump oil had to be this specific compounds, just in case sulfuric acid got in there, it wouldn't destroy the oil and destroy the pump. So she set up the system, and she went about taking sulfuric acid, putting compounds in it, evaporating the excess sulfuric acid to recover her compounds. So she did that, and at one point she went around and she took, remember I told you about the amino acids? And I told you about the nucleic acid bases? And she would put that in sulfuric acid, evaporate the excess sulfuric acid, and after the excess sulfuric acid was gone, there was always the tiniest bit of liquid left over. It would not evaporate. Unfortunately, so I just want to let that land for a moment, because I hope everyone here gets that moment. Now, most of us get a moment when something doesn't go according to plan, but usually something was wrong. How many times your code was wrong, or you just experiment didn't work out. And she kind of, I think that's what she thought happened, but fortunately she didn't throw it out. She brought it to the team, and someone on the team realized it's an ionic liquid. What happens is, earlier I was trying to emphasize that sulfuric acid wants to donate a proton, but the nitrogen on these organics wants to receive a proton. So after the excess sulfuric acid is gone, you're left with a negative, the hydrogen sulfate, and a positive, the organic molecule that's now got the extra proton, and they lock together an ionic bond, which is so strong that it really doesn't evaporate. Now, if anyone here came from the space side, there is ionic liquid used in space in electrospray propulsion. There's a little bit of it used, and people have heard about it. You need to put a kilovolt into it to split it up, and it sprays out the thruster. It's really hard to destroy this stuff. So what are ionic liquids? They are liquids, they're salts, essentially. They're held together by ionic bonds. They are liquids below 100 degrees. There's literally 1,000 of these known in industry. They're they're not very well known, but they're kind of like their own industry in and of themselves. But this is the first time anyone has recognized that they can come out of planetary materials, sulfuric acid and nitrogen-containing organic molecules. In our solar system, our asteroid series is covered in organics. Even Mercury has organics at the poles. The origin of life people have a way to make nitrogen-containing organics, starting with HCN, and have multiple pathways. And so we're arguing that these ionic liquids may exist on some planets. Here on Earth, we've got sulfuric acid coming out of some volcanoes and vents. And they just literally have to come together and will make these ionic liquids. So what's so fascinating about these ionic liquids is they have very low vapor pressures at room temperature, as low as 10 to the minus 15. So that means that as far as liquid goes, you don't need a giant ocean or a Great Lake, because they're not going to evaporate. You just need little amounts of them. and they can persist over time. So, usually when I tell people about it, it's just sort of hard to get your head around why we're just so jazzed about it. But I want you to know that they still form, even like on rocks here on Earth. We form them in the lab. Because as long as you can get rid of the excess sulfuric acid, not just by evaporation, but it will like seep into the rocks, you can be left with an ionic liquid. So the reason we're really jazzed about this is biomolecules are known to be stable in some classes of ionic liquids. Like we have put DNA in the ionic liquid and it is okay. Some ionic liquids have been used for subcutaneous drug delivery. I wouldn't put this one under your skin. Yeah, so it's like a new field. We're pursuing this idea that maybe they exist on some exoplanets. Here's like a laboratory spectrum of them. For now, we don't have a way to detect them on exoplanets, although we know the IR spectra. But we're still trying to pursue this idea that there's a large range of planets that could have liquid sulfuric acid. Here is a pressure, temperature, phase diagram. You're familiar with like pressure in atmospheres and temperature in Kelvin. This is water. This purple curve is water. So you have Earth. Mars is too cold for water. Venus is too hot for water. But this purple region is actually where sulfuric acid is stable as a liquid, actually. It's kind of a very, very vast region. I just showed these pictures. We went to the field to do some lab work. And out of this, some of you have been there to Volcano National Park. Out of this vent, there's sulfuric acid coming out of it. So I have a lot more to say about that, but I will leave that like for the questions and for the wine and cheese discussion after. But to summarize this part of my talk, ionic liquids. Exoplanet detection techniques have shown us that there's huge numbers of planets. They're going to be too warm for water. They're too warm for water. They may not even have an atmosphere. These ionic liquids could exist like in crevices protected from high energy particles. There could be these life-friendly liquids out there somewhere. Well, I'm going to get to the end of my talk now. And I thought I would show you this video that my postdoc Yarrow went to a field site that has a sulfuric acid lake, not like pure sulfuric acid, just like a little bit of sulfuric acid. It's in Indonesia. And just want to let your mind wander. I hope that you can go on a journey. This is an artist's conception where, the impossible can become possible. So now I will summarize from lab to cosmos, 3 frontiers in the search for signs of life beyond Earth. Venus, the possibility for life in the clouds. New space missions, like focused space missions that can just go after one problem, especially if we can launch these miniature molecular sensors designed for targeted molecules. And I finish with exoplanets, trying to expand our minds about what kinds of planets could be habitable. Thank you very much for your attention today.
Very much, sir, for the great inspiring talk. Questions? Yeah.
Thank you for the talk. I have 2 questions about the first 2 parts. So about the amino acids. In life, they're like the neutrality of biological conditions is important because the first peak of amino acids is around 2.3, second one is around 9.5, so around like neutral pH, you have like 2 ionic states for amino acids, right? And in sulfuric acid, they're mostly going to be protonated. So although they can survive, their functions are going to be not the same, or probably not going to work the same. So what do you think about that part? And the second is the fluorescence technique that you're planning to use for detection of organics. It appears like the amino acids that got destroyed in sulfuric acid are the ones with aromatic structure, like tryptophan and phenylalanine. They're going to be the bright ones. So, and those seem to get destroyed.
Okay, yeah.
What is
There's 2 separate questions. So we're just like at the tip of the iceberg of what we're doing here. In fact, we need people like you to help with all this. Because I sometimes try to wonder, like, what is the most primitive type of life? What functionality does it really need? I really don't know. We're not there yet. We're not trying to get all the answers. We're just trying to motivate going to Venus. So I don't know about those amino acids. We're working with peptides now. We'll stay tuned. I mean, the best thing I could do is convince you to work on this. As far as, I conflated a lot of different things. We're not necessarily looking for amino acids right now. We have some other extended team members. Some people might know Steve Benner, and they did the work for us for our detector, like to find out what wavelength should we choose for fluorescence and which detector range should we choose, given that we can only choose one. And they found that if they put a small seed molecule like formaldehyde or some others in sulfuric acid and they heat it, it will like grow into a rich organic chemistry. So it wasn't that we're looking for amino acids, we're looking for aromatics of some kind, which we think could be there for fluorescence. Yeah, but it's not ideal. One of the miniature molecular sensors we're onto now is UV fluorescence, but measuring the time decay. Because there's more information in the time decay. There's people who measure like at the nanosecond level, like exactly how it decays. So we're trying to do a more sophisticated version of UV fluorescence, but I agree with the amino acids, yep. Yes.
So another place where ionic liquids might be present is Jupiter's moon Io, because it's very volcanic and there's sulfur and sulfuric acid possibly, although the hydrogen's probably gone. You thought at all about trying to look for these in some way? You mentioned their spectral signatures, but you didn't say specifically where they are. It would be hard to do that, probably not possible with JWST because I was too close to Jupiter, but maybe with some ground-based spectroscopy. What would you do?
I would say let's do it. Now, one thing is that these ionic liquids, they do freeze by Io's temperature. That's the only problem. So we may be able to look for them, and they wouldn't be like a habitat for life there, but they would be frozen if they're there.
Yep. Near the areas that are actively emitting lava, which are warmer.
Yeah, I would definitely love to look for them. I would really find that very exciting. Let's, we can get like the next question and I will go back to the, whoa. And it's published, so you can go and look at our figure, but, and they're not going to be these like giant features. It's just because this is in a laboratory setting and it's like a pure compound and it's like directly there. But you can see the blue is what you're looking at. This is OH. And then this is, infrared here. So you can see wavelength in microns. It's definitely got a signature, so I think this is a really great idea. Yeah.
Obviously that water enables a host of different chemical reactions that can take place in it.
Yeah.
Is this true for ionic liquids as well? Or specifically the ionic liquid that you were describing, the sulfuric acid?
I think, I'm not going to say stuff like I'm not like knowledgeable enough about, but I think so. Like people who, there's like books on this stuff of people who have like done conference articles and conference proceedings about people putting molecules like enzymes in there to see what will happen. But this is like the beginning of a long journey. So we're going to experiment with all that. Yes.
What drives your interest toward Venus as opposed to the icy moons or Mars?
What drives my interest to Venus or the icy moons or Mars? I just want to say I love all the planets. And Mars, wow, I sure hope there's life right subsurface in Mars. Maybe there's even some kind of other types of, there's like briny salts there. There's a lot going on in Mars. Enceladus, Jonathan Looning here is an expert there. Like I honestly got involved with Venus because of the phosphine on Venus. Does anyone remember the phosphine story? I should just tell it to you briefly. Like I've worked on exoplanets my entire career. Like a lot of growing number of people wanting to find signs of life on an exoplanet. So like literally about 20 years ago, I set off to write down every possible molecule that can be in gas phase at room temperature and pressure. Because there's a whole lot of molecules made by life on Earth, like isoprene or like some very obscure things. Isoprene is pumped out in as much quantity as methane. But we don't always know the reason why. So I felt like this giant journey and made a giant framework and put students on it. And the favorite gas that popped out of what elaborate framework we probably didn't need for this was phosphine. Phosphine is, on Earth, phosphorus wants to go with oxygen for phosphates. We have little hydrogen here. It's thermodynamically disfavored. And we started writing a bunch of papers about phosphine and how this should be a good, great gas for exoplanets. On Earth, it is made by us as pesticides. It is found in oxygen-free environments. And I got connected to Professor Jane Greaves, who across the globe, oddly enough, was also working on phosphine, a gas that most astronomers and physicists just never really heard of. So I started working, my team started working with hers on this whole phosphine on Venus, and it ended up being incredibly controversial. It went out there and was just kind of dismissed at every level. Is the signal real? Is it attributed to the right gas? Is it a sign of life or something else we don't understand? But that's what sucked me into Venus. So it was really just, you know how oftentimes you kind of do the random walk through life. It was like the phosphine and going back to Venus. And the phosphine, honestly, it shone a new light on Venus. And many people now who never worked on Venus have started to work on it. So I do like all the planets, but I wanted to share my personal story of how I got locked onto Venus. Yep.
You'd mentioned, I think particularly with the ionic liquids, like potentially existing in like a crevice to be protected from, high energy particles or whatnot. But then to the like summary of the first part, thinking about like life in, the upper atmosphere or something, I could see those high energy particles also being almost like enabling of some type of chemical reaction. So do you have any insight into like the interplay between it being damaging versus actually helping?
Yeah, it's a tough one. A lot of people think we needed high energy particles or high energy UV to like make reactions happen versus not making it happen. So the one thing about ionic liquids is I really wanted to pursue an idea of like an airless body and having a liquid there. But it's not clear if that could last there because of high energy particles breaking it up. So we put this ionic liquid under an electron microscope, and it's essentially being bombarded by like super high energy electrons. And oddly enough, it like made a hole in it, and then it self-healed when we turned the beam off. But the edges of it started to bubble and react. So I don't really. Everyone in the origin of life or astrobiology has their own opinion about is high energy bad or good. Yep.
Maybe then let me ask. So what are the steps that are needed for the Venus missions to scale up, and then finally when can we book it?
I know you're going to laugh when I say this, but we really just need money. I mean, it's just literally a matter of money and time. And I was talking to Professor Judy Su here, but it takes a long time. I know here there's a lot of amazing quantum things going on, right? But they're large, like tabletop experiments with lasers and all sorts of things. And you have to ask yourself, how do you shrink that down to like a little photonics device? And people are doing this, but it's not really mature yet. So we need some time and money to figure out which of these miniature molecular sensors will do the job for us. And the other parts, have been done before and could easily scale up if we can. Yep.
Have you worked with other assets? Because like I was like thinking I'm working on Ceres and like we have
Oh, wow.
carbonates, right?
Nice.
Like this, we may even have like brines and we have spacecraft data.
Right. Well,
All
yeah.
those like bright.
Very nice. Yeah.
So do you
Have we worked with other acids? Have we thought of other possible ionic liquids? Yes. We've tried so many combinations in the lab now, and we can definitely talk more about that. Yes.
No more questions. We'll pass the hour. See you all.